So I would like to first mention my collaborator, Andrew Gattelman, who was supposed to be here, but Professor Xu just realized Thursday and Friday are national holidays, so he's now in Kyoto, I believe. So this work was done, funded by ACRIT, by the FAA. ACRIT stands for Aviation Climate Change Initiative. So we basically use CAM5 to study the radiative forcing for contrails. So it's just a quick outline. I'll start with some background introduction. And then CAM5 doesn't really allow you to assess contrail radiative forcing. You need to put in something. And I'll show results from our simulations and conclude. So just in case, people probably don't know what contrail means. This is a picture taken. One consequence after I got my smartphone, so you can take pictures whenever you want. This is taken in early March outside of my parking lot at my gym, because you can see this line-shaped cirrus. It's obviously there's probably an aircraft here, and so you might wonder, what triggers the formation of contrails? Basically, based on observations, there are two criterion. First one is the ambient air has to be below some critical temperature at a given pressure level. And that ambient humidity has to be ice saturated, and that's what governs the formation of contrails. And this is work previously done, and the radiative forcing actually is pretty small if you look at the global average. And this appears in AR4 by Lee et al. So, okay, when we talk about contrails, you can, like, for example, when the contrail just formed, you can actually define that as linear contrail because you can still tell it's very fresh, very young. But as you can tell at the tail, it starts to spread. And you can't really tell later. You don't know if that's part of cirrus or contrails. We call that contrail cirrus. So for linear contrails, in the previous study, it's about 12 milliwatts per meter square, global average. And just give you an idea, for a doubling of CO2, the radiative forcing is about 4 watts per meter square. So this is a very, very small number with very high uncertainty. For contrail cirrus, it's about 33 milliwatts, not watts, per meter square. Again, this is just a very, very rough estimate because at the time we didn't really have the capability to simulate that in GCMs. And you might wonder why we care. If we care about CO2, this is CO2 emitted by aircraft. It's actually 28 milliwatts per meter square. So it's actually on par with contrails. And the latest study by Berhardt et al., they come up with a number of 31 milliwatts per meter square. So it's pretty much consistent with this AR4 reports. They use ECAM5 for their study. And since CAM5 now has the capability to simulate ice supersaturation in the upper troposphere, lower stratosphere, so we were actually asked to perform this study to see what CAM5 really says. And we performed two sets of simulations. The first set is so-called diagnostic calculation, because the signal by the linear contrails is so small, so we can't really do a fully kind of free running CAM. I will get to that later, why you can't use free running CAM to do that kind of study. And we also obtained aviation emission inventory from the FAA with a global coverage hourly data for year 2006. We actually converted the data into monthly, daily, and hourly input just to test if we do require that emission of very high temporal frequency, or we can get away with monthly input. So here's the fairly easy contrail initialization we put into CAM5. So first you put in the aircraft water vapor emission into the model and go through the Schmidt-Appelman criteria to determine if contrail formation is possible or not. And if the criteria is not met, then the water vapor will go into the background water vapor field. If contrail formation is possible, then you have to up the cloud fraction by this amount. This is aircraft water vapor emission divided by in-cloud ice water content of contrails by an empirical function given here. And then you have to also up the number concentration of ice particles. We assume, probably not a bad assumption, but we assume all the ice particles are spherical. And based on an observational study in year 2000 by Schroeder et al., for young contrails of 30 minutes, the particle size is about, in terms of diameter, it's about 10 microns. That's what we assume. But a major contribution for the ice mass in contrails is actually from the ambient air. It's not just from the aircraft emission. So basically, when contrails just formed, you actually suck in the water vapor above ice saturation. So you have to make an assumption. We got the flight track distance from the emission inventory, but you have to make an assumption about the cross section of contrails, because you need to figure out how much ambient water vapor you will get into the part of the contrails. And in this study, we assume it's 300 meters by 300 meters. And here's just a quick look on the aviation emission. This is field burn. And on top is the zonal mean plot for January on the left and July on the right. So there's no surprise. You see the biggest maximum emission over the mid-latitude in the northern hemisphere. That's consistent with our experience. And at the bottom, you have the top view at about 230 hectopascal, where you see the most flight tracks. As you can tell, you probably can even see very clear tracks how at least I got back to Taiwan about a week ago. So a lot of aviation aerosol emissions are actually scaled based on field burn. Water vapor too. I can pass this. Okay, here's the challenge. Before you use a GCM to do any kind of radiative forcing study, you have to know the limit of your tool. So if you do a free running Chem5, the internal variability of the model is about 0.1 watts per meter square. It's way above the forcing of contrails, either linear contrail or contrail series. So the original idea from Andrew was like, okay, you do a contrail simulation without aircraft emission. Then you do an experiment with aircraft emission. Then you take the difference, and the job is done. But if you go that route, you're going to get noise, because the model cannot pick out the signal so low. So what we did was like, there's another mode we can do in Chem. That is, you run it in so-called prescribed dynamics. So the dynamics is, you nudge the dynamics based on some observational product, or what we did here, just use the free running Chem and output every 6 hours and keep nudging the background dynamics into that product. And so you kind of eliminate some degree of freedom. So here's a plot of that. Just maybe look at the solid curve for now. This is duration of simulation for 20 years. By the end of 20 years, in order to get past 95% confidence level, you only need to be above 10 milliwatts per meter square. So this framework, this modeling framework might be suitable for the study of contrail series. But for linear contrail, the previous study shows actually the forcing is still below this. That's why we have to come up with another approach. That is to incorporate the aviation emission into the model in a diagnostic fashion. So you include the emission into the model at every time step, assuming the emissions or the contrails never interact with the basic state, the baseline model run, and throw things out at the end of each time step. And you have to assume, that's why we have to assume the lifetime of contrails is only 30 minutes. That's the best we can do. However, even doing so, you have to be aware there are a lot of uncertainties. For example, the background meteorology you use to nudge the model to. So to address this, we use the so-called ensemble modeling technique. So we use 4 different yearly meteorology obtained from a free-running Chem5 simulation previously. And so you get 4 ensemble members. And you run the model for 20 years individually. So you get 4 ensemble members. So you can get an ensemble mean. You can get a standard deviation. Second uncertainty is actually ice particle size in contrails. As I shown earlier, for young contrails, the diameter of ice particle is about 10 microns, but it's not exact. And we found out if you choose a slightly smaller number, you can up the radial forcing almost linearly by number concentration. Third is actually the cross-sectional area of contrails. We assume it is 300 meters by 300 meters, which gives us the best fit. When we did this simulation for linear contrails, we got the contrail coverage, global coverage, which is compared with MODIS data retrieval. We got the best fit, but it doesn't mean this is the best number. So just be aware, even after the simulations, there's these uncertainties. First, I'll show the so-called instantaneous effects. This is by linear contrails. This is a pretty busy plot. So I'll look at the first column is the global ice mass globally over the eastern US and Europe. The solid line represent the ensemble mean using hourly aircraft emission, and dash dotted lines are from daily and monthly output. You can tell the diurnal cycles are very different when you use the hourly input versus daily and monthly, and which is pretty much consistent with what's shown here for the long wave in the third column. And the second column is the short wave. Short wave, actually, Contrail has a net cooling effect based on short wave cooling. And when you use hourly input, you actually get more intense cooling. So in order to reduce the risk of generating global warming, it's better to take a day flight than a night flight. That's if because people actually talk about mitigation, how we change the aviation industry to reduce global warming. This is the implication. You need to take better flight during the day than at night. And this is the last column is the net forcing. So the take-home message is that if you use daily or monthly output, you are likely to overestimate the warming effect. So it's better to stick with the hourly input. You really need high temporal frequency for aircraft emission. And this is just an annual average. And so regionally, over like Chicago, for linear Contrail, local impact could be as big as 0.1 watts per meter square. Over Central Europe, it's about twice as much. And if you look at monthly average, I don't know if you notice, try to pay attention from now on. You will see more contrails in the winter because the temperature in the upper troposphere is lower. So you tend to get more contrails in the winter. I'll jump to the integrated effect, or linear contrail series. The same message, basically, for monthly average. For the regional impact over Chicago area, it could go up to about 0.3, 0.4 watts per meter square. In Central Europe, it can be as big as 1 watt per meter square. This is pretty much on par with the radiative forcing of anthropogenic CO2. So when you talk about contrails, if you look at the global average, it's totally misleading because the impact is very isolated. So here's the number we come up, very different from the previous studies. For linear contrail, it's about 2.9 plus minus 2 sigma 0.5. That's quite a bit lower than AR4. For Contrail series, it's about 13 watts per meter square. So here's the summary. So I think I got confirmation from Ziling. She used to live in New Hampshire. She told me she noticed a lot of contrails over her head in the winter, and that's true. Opposite from what I thought before I started doing this. So, because I thought there's more water vapor in the upper troposphere in the summer, so it get more contrail, but that's the opposite. The temperature effect is more important. And the second is diurnal cycle of flights is very important. You pay more if you fly at night. It will create more warming if you fly at night flights. And the integrated effect, or the radiative forcing for Contrail series, is about 5 times bigger than the effect of linear Contrail based on our study. And the regional impact is much, much bigger than the global average, as I shown, because if you happen to live in an area where air traffic is very heavy, locally, the impact can be as big as the impact from the anthropogenic CO2. For the future work, we're now almost done, but not quite ready to show. The FAA provided us with several different scenarios for the future aviation emissions. And then currently we're doing simulations using those projection scenarios on top of the RCP simulations. And the impact should be bigger. But there are two competing factors. One is, in the future, the air traffic gets heavier, but the air temperature could get higher. So it might prohibit contrail from formation. So there are two factors. It doesn't necessarily mean if you get more emissions, the radiative forcing for contrails will get bigger. So we're now assessing that now. So that's what I have today. I'll take questions.
And we can take 2 questions.
Yeah, I was curious, you mentioned quickly 30 minutes lifetime of contrail. I guess probably that concept came probably from a model's time step.
Yes.
I was curious because, the current GCM, the grid lifetime, or if you call that, it's about 1 day. So if you use a 2 by 2.5 or even 1 degree. So, and then in between 30 minutes lifetime and a day, there's a huge space, which build upon a typical, very classic scale issue. Whether you should looking at which scale for the climatology. I'm curious how sensitive that would be.
Current understanding is that the lifetime for linear contrails is probably at most a couple of hours. Beyond that, you either die or it migrates into contrail series.
That's an ice
Yeah.
crystal.
Yeah.
If the Gaussian film still keep the sign, but that's water vapor and many particle aerosol. So these are invisible.
Yeah.
Yeah. So
But we did do a simulation just to look at the impact of aviation water vapor, meaning no contrail formation, and there's almost no impact, or at least it falls below the noise level. So there's always a limit what you can pick up in a GCM. So
Okay, second question.
Can you Get back to slide number 3. When I was visiting Weichang several years ago during my sabbatical, I was sitting outside in the afternoon looking at the sky.
Yeah.
And I saw a lot of those contrails.
Yeah.
Now you show only one, but
Yeah.
behind the contrail, you see those cirrus.
Yeah.
Those are actually cirrus contrails.
Well, if you fly high enough, you probably can still this line shape.
Sometimes
It's still young, so you probably can still define that as a linear contrail. If now it's blocked by probably
Right.
lower level cloud, because I believe this is younger, this is probably older because it starts to spread. You can tell. So
And actually, the one on the top is, I think they are very likely contrail because I was sitting there
Yeah.
and see the contrail develop. They
Yeah.
lasted actually hours.
Yeah.
The
Yeah.
whole afternoon, several hours.
Yeah.
And then the whole sky spread out.
Yeah.
They are all contrails. So I just wonder how you deal with that in the model. What is the cross-section area and what is the
Okay.
overlap?
So in the second set of simulations, we don't make any assumption for the lifetime of contrails. Once it's formed, it actually becomes part of the cloud. So it will just evolve later itself. We don't make any assumptions. So in Bernhardt et al., this is in Germany, in DLR, they spent years to putting their contrail polymerization. They have a different species of clouds called contrails, and they have a mechanism to transform contrails into cirrus, but we didn't do anything like that. We don't have a separate species for contrails. So meaning that the evolution of contrails in the second set of simulations is basically unknown. Once it's initiated, it will just fully evolve. It could die, it could do whatever. So, yeah.
Any other questions? Okay, let's send speaker again.